Hello everyone, so in this video I'm solving section C of the data science internal paper, and this section C revolves around the topic of deep learning. And with the question number 26, it talks about deep learning versus machine learning. So let's understand what it says. So starting with the section C, here we go. So people often use AI, machine learning, and deep learning as synonyms, but they aren't the same. It's like a Russian nesting doll, where the big doll is the AI here, and machine learning is inside it, and deep learning is the part that uses neural networks, and it's the smallest, more specific doll inside the machine learning. So what did you get? Deep learning is not a synonym. It's a specialized subset of machine learning. Yeah. Question number 27 addresses a big claim that can a computer really understand and learn any pattern? So, like, can it predict stock prices and recognize faces? And can it drive a car? That's a question. So, ideally, yes, this is a mathematical proof that says if a neural network is big enough, it can mimic any curve or a function in a universe. Like, let me read it once again. That there is a mathematical proof that says if a neural network is big enough, it can mimic any curve or function in the universe. Means AI can learn patterns and actually drive a car like Tesla do. So neural networks are the universal approximators of functions. Like neural networks are really out the boss. So moving to question 28, we look at a structure. A basic network has an input, an output, and maybe one processing layer in the middle. But what if the problem is really hard? So there, we stack more and more layers in the middle to solve complex problems. But the word deep literally just referred to this stack of the layers, where a network with more than one hidden layer is termed as deep and deep neural networks. Let me read it once again for you all guys. For this question, a basic network has an input and output and maybe a processing layer in the middle, right? But if the problem is really hard, so we stack one more and more layer in the middle to process that problem, right? So in the middle to solve a problem. The word deep literally just refers to this stack of layer. So this deep neural, so this deep layer is a network with more than one hidden layer in it. So that's what we call deep neural networks. That is used when we have to solve a very complex problem. And there, question 29. So it's about the flow. Imagine a bucket brigade putting out a fire. The first person passes the bucket to the second person. Sorry. The neural network works the same way. Like neural network not don't actually passes one bucket to the another bucket, but it works the same way actually. Not exactly passing on the buckets, but the flow of work is same. Those So the result from the first layer ain't the final answer. It gets handled off to the starting point of the next layer, and each layer's output becomes the next layer's input. So it's a simple thing. When you're passing a bucket to the second person, the the hands that are empty before gets filled with the bucket that came from the another person's hand, and when you hold it, it becomes the input for you. So now comes question 30, CNN, convolutional networks. So what are these? So in short, CNN are used to classify images. It is used for classifying images. So as you can see that standard networks are bad at seeing images and pictures. So if you saw, for example, if you move a cat face straightly to a left, or a normal network gets so confused. So we need a network that scans images in a grid style, right? So like a sliding window to recognize patterns anywhere in the picture, CNN is used. Question 31, RNN, recurrent neural networks, where I want you to imagine reading that you are reading a sentence where you can't understand the last word unless you remember the first word. Standard networks have no memory of the past. Recurrent networks have a loop inside them where they pass information from the previous step to the current step allowing them to understand time and order, where RNN handles data with strong sequential or turmoil dependencies. Question 32, long short term memory, LSTM. So the problem with the basic RNN is that they have a short attention span, like humans nowadays. They forgot the beginning of the long paragraph by the time they reach the end. So we invented a smarter version with a special save button that let it hold onto important memories for a long time. LSTM, long short term memory, is a improved version of recurrent neural networks. Question 33, GAN, generative adversarial networks. So question 33 is about creativity. So how do you teach a computer to draw? Actually, how do you teach a computer to draw? It's not a kid that you hold, that you give it a pen and say that draw a line like this from connecting one point to another, draw a line like this. You can actually do this, no, right? It's a machine. So how do you teach a computer to draw, right? So you might make it a game. You make a game, okay. So one AI tries to draw a fake and another AI tries to spot the fake. The second AI acts like a police officer or an art critic that forces the first AI to get better and better with until the fake looks real. That's something very very interesting to actually know about it. That generative adversarial networks are doing this thing. Like one AI is teaching another AI how to make predictions and how to make a line. So in a GAN, generative adversarial network, the second model acts as a discriminator, distinguishing real and fake data. Question 34. Question 34. And I want you to imagine that you're learning how to drive a motorcycle and you don't need to relearn how to balance it. You already learned that when you rode a cycle, right? In your childhood. So there is no need for you to actually learn how to balance a motorcycle. So AI does the same thing. We take a model that already knows that how to see shapes from a huge data set, right? So we just teach it the specific details for a small task. Reusing a pre-trained model for a related task is called transfer learning. Like the model knows things from their previous experience, but all we do is that we just give it the pre-trained data, and now with that it trains itself. Question 35 looks at recommendation systems. Sometimes we just want the model to remember obvious rules. If user buys burger, recommend them a fries, but I hate fries. Bhai. So the wide part of the model is a simple linear formula designed to learn this direct, frequent co-occurrence. The wide part of a wide and deep model helps memorize specific examples. Let me read it once again. So look at the recommendation system. Sometimes you just want a model to remember obvious rules. Like if someone asks for burger, they might ask for cool drinks or fries. So recommend them with that. So also the wide part of the model is a sample linear formula designed to learn the simple, direct, frequent co-occurrence. That just look at the frequent recurrence with this thing. Like for example, if someone is going for their purchase of the car, if someone purchases a car, the customer handling team will ask them to buy accessories related to this thing, buy the seat covers, install this perfume in our car, because they have seen a pattern in person in real life, that those people have seen a pattern that if someone is buying a new car, will they will buy these things for sure. That वो लेंगे ही लेंगे. That's a permanent thing, that they will buy a seat cover or a perfume for their car. So the wide part of a wide and deep model helps memorize a specific example. Question 36. But what if you want to recommend something new? Just memorize the past isn't enough, right? What if some person wants to buy new wants to buy new alloy wheels for their car from another retail store, but not from the showroom. So it's their choice, right? So what if you want to recommend something new? Just memorizing the past isn't enough. The deep part of the model looks for hidden. The deep part of the model looks for hidden abstract connections, like realizing that people who buy sci-fi books might look for tech gadgets. The D part captures more general, more abstract features. Like it's like if someone is a F geek, they might go for a flight experience more often than the normal people who sit at home. Cause that F geek guy always wanted to see aircrafts, and he will actually go to planes and sit in it and have a roam around in a city, sorry, country. ये थोड़ा घुमक्कड़ टाइप होगा. And yeah, he will always look for aviation toys, like AirAsia sells those plastic airplanes, right? So he will always looks for having that thing. So here comes the turn for the question 37, where it takes us back to the algebra phase, where neural network is basically a giant math equation, which is y is equals to mx plus b, where the network learns by tweaking the slope m and intercepts b until the answer is correct. In AI terms, we call this weights and biases. So the linear classifiers combines input with weights and biases to form a prediction. So that's where this algebra comes into the play, where the linear classifiers combines input and with and forms predictions with weights and biases. So coming to the 38th question, which is on activation functions. So here is the issue. If you stack 100-layer linear equation, we still just get a straight line. Oh, so what? But the real world is curved and complex. So we inject a special function, just like a switch, the bands and the line. This follows the neural network. So here comes the turn for the question 37, weights and biases. So neural network is basically a giant math equation which is y is equals to mx plus b, where the network learns by tweaking the slope m and intercepts b until the correct answer is gained out. So in AI terms, we call this weights and biases, where linear classifiers combine input with weights and biases to form predictions. Question 38 is the next, on which we are going to talk about activation functions. So here comes the issue. If you stack 100 linear equation, we still get the straight line, but the real world is curved and complex. So there we inject a special function like a switch that bends the line. This allows the neural network to learn complex shapes. Activation functions introduce non-linearity into neural models. Question 39, we are going to talk about capacity. So think of a model that has a model's brain size, sorry. So think of a model's brain size where a small model can't learn quantum physics. It's too simple. If we add more neurons and more layers, we are giving the model more brain power to understand difficult patterns. Adding neurons or hidden layers increases the model capacity. Question 40. Question 40. This is the last question of section C, and in this we are going to talk about pre-trained features. So training a huge model like GPT or NestRes cost millions of dollars and lots of human efforts too. But you can't do that thing on your simple laptop, right? Instead, you download the brain that Google or Facebook already trained. You use the feature they already learned, so you don't start from zero. So transfer learning leverages pre-trained features learned from the prior task and put it into your own version. So thank you for watching this video. This is the section C last question, and we are done with the section C part, and thank you for watching this video.